Hello, everyone. Welcome to discussion in week 10. Today's topic is operational amplifiers, which corresponds to chapter 14. After the discussion today, you'll be able to know the characteristics of an operational amplifier, and you'll be able to identify a negative or positive feedback. And most important, you can use the summing point constraints to analyze the circuits with an operational amplifier with a negative feedback. Okay, so before we go into any details, let's talk about the basic idea. What is an amplifier? Suppose we have an input signal and we want an output which has the same wave shape, identical wave shape as the input, but with a larger amplitude. We can write it down as an equation of VO of t equals to A of V times VI of t. And the output voltage is usually applied to a load resistance. When the A of voltage is positive, we say that it is a non-inverting amplifier. If A of V is negative, you notice that the phases are opposite. So we say that it is an inverting amplifier. This is what we need to know before we go into an operational amplifier. An operational amplifier usually consists of about 30 BJTs or MOSFETs, as well as about 10 resistances and some capacitance. They are as cheap as the discrete circuits, but performs better. In other words, it is economical to use operational amplifiers, also known as integrated circuits. Alright, this is a background. And why we call it operational, this is because this kind of amplifiers, this kind of circuits originated in analog computers where these circuits are used for operations. We'll encounter an example of performing an operation with operational amplifiers later. Alright, the op-amp has two input terminals. We call it VP and VN, positive and negative. And it has one output terminal. The amplifier itself is also connected to power supply. But usually we don't explicitly show the power supply in the diagram. VP is also called non-inverting input. The VN is usually called inverting input. Another term, differential input signal, is defined by VP minus VN. Alright? Before we talk about an ideal operational amplifier, let's look at a realistic voltage amplifier model. This part is not required in exams, but it will help you understand the concept. Suppose we have a source connected to an amplifier as a black box, and then the outputs are connected to the load. Pretty straightforward, right? And then, if we try to represent the things hidden in the black box, we'll have a more detailed diagram that looks like this. Ri is the input resistance. RO is the output resistance. RS is the internal resistance of the source. To simplify the problem, let's ignore it. Alright, so the original black box, is expanded in this way. When we say an ideal operational amplifier, we are actually saying that we want the input resistance to be as big as infinity, and we want the output resistance to be as small as 0. And we want the open loop amplifying factor to be very large, like infinity. In this way, the output voltage will not be dependent on the resistance load. Up to now, we haven't talked about summing point constraint yet. Don't worry, we will cover it when we talk about the inverting amplifier. An operational amplifier combined with source resistances can form many kinds of circuits for different applications. In the last section, we know that an ideal opti amplifier has a very large AV. To restrict it to some finite values, we need a feedback loop. With the feedback loop, we can use the summing point constraint and KVL, KCL to calculate the expression of AV. If the AV is negative, we say that it is an inverting amplifier. When the AV is positive, we say that the circuit is a non-inverting amplifier. Let's first talk about an inverting amplifier. So usually, we analyze negative feedback operational amplifier circuits with such an assumption. They are ideal operational amplifier. This is usually accurate. And then from the characteristics of ideal amplifiers, we can derive summing point constraints. Then applying KVL, KCL, we solve the circuit and get the expression of AV. To summarize, the first step should be verifying if a negative feedback exists. The second step is write down the summing points constraints. Step 3 is to apply what we know about solving a circuit and get it done. Let's go through the step one by one. In the first step, how to determine if a negative feedback exists? The rule is, if the output is connected to the inverting input terminal, we can say that it provides negative feedback. And intuition is, we have minus and plus, and this is the output. If we have a wire, maybe has a resistance on it, and then connect it back to the inverting terminal, we say that it is negative. If it is connected to the non-inverting terminal, we say it is positive. Alright. How do we derive the summing point constraint? We don't need to derive it when we solve it every time, but I would derive it here to help you understand. When we have a link from the output back to the inverting input, we will notice that the inverting input will increase a little bit by the output because the output is very large. It is infinity times something, right? So the Vn will goes up in a very short time, which results in a decreasing differential input. And then, because input decreases, the output will also decreases a bit. So you can see that the output is in opposition to the input. We say it is negative because the open loop A is very large. Only when Vn increases to Vp minus Vn approximates to 0 will the output voltage become finite and stable. In other words, we say that Vp approximates to Vn. It is the same to say that Vid approximates to 0. Because the voltage are approximately the same, we can say that the P and N are almost shorted, right? Because they are almost shorted, we use a dashed line to represent the almost short relationship. The things in the green circle will almost be shorted. That is to say, the IN and IP here are almost 0. Does it make sense? Great. Here, we already get the summing point constraint. Vp equals to Vn and INIP equals to 0. Let's try to apply it to some circuits. Exercise 1. A summer, which is a circuit take the sum of the input. Step 1. Is there a negative feedback? Following my cursor, the output is connected to the inverting input, right? So there is a negative feedback. Step 2. Because it has a negative feedback, we can apply the summing point constraint. This is Vn, this is Vp. We can see from the diagram that Vp equals to 0 because it is connected to the ground. And Vn equals to Vp equals to 0, right? And the In, Ip are equals to 0. We can just ignore it. Next, step 3. We can do the circuit analysis based on step 2. For example, at node star, we can write the KCL equation, which is VA over 1K plus VB over 1K plus V output over 1K equals to 0, right? And if we write the output voltage in terms of the input voltage, we will have something like this. VO equals to minus VA minus VB, right? So the function of this circuit is to take the sum of VA and VB and flip it. Interesting? Congratulations that you're able to analyze a circuit with summing point constraint. Let's do another exercise. Exercise 2. What do you think of this circuit? Yes, you're right. We cannot apply summing point constraint here because we notice that it is actually a positive feedback rather than a negative feedback because the output is connected to the non-inverting input. To be more specific, when the differential input increase, the VO will increase, which feeds back to the non-inverting input to make the input grows even bigger and aids the output to grow rapidly. This circuit will quickly saturate at extremes. A lesson here is to verify negative feedback first. Nice. Next, let's come to non-inverting amplifier. Quickly remind you that the definition is AV is bigger than 0. Okay, so let's do exercise 3. Question. Please compute the AV when the switch is off and on. Also, compute the input resistance when switch is on and off. Let's first consider the case that the switch is off, as shown in the diagram. First, is there a negative feedback? Yes, because it is connected to the inverting input. Negative, check. And then, what is the summing point constraint? Here we see that IP equals to 0. IN equals to 0. Because the switch is off, we conclude that I2 equals to IP equals to 0. That means that no current is flowing in the red branch. Since no current flowing, there is no voltage drop, right? So the voltage along the branch is always VP. Therefore, we can write the equation of I1. I1 is actually equals to VR over R, right? And the VR here is VP minus VN over R. From the summing point constraint, we know that VP equals to VN, so the I1 is also 0. From the KCL, we know that the input current is equals to I1 plus I2. They are all 0, so II is also 0. Similarly, we can derive that I3 is equals to 0, too. All of these are 0. So no voltage drop across all the R. Applying KVL to the outer loop, we'll find that VO equals to VIN. That is to say, the AV equals to 1. We can see that it is positive, right? So we say that it is a non-inverting amplifier. How to compute the input resistance here? The input resistance should be equal to VIN over I input. Since the I input here is 0, the input resistance should be infinity. Great. Now let's consider the case that the switch is on. Let me copy the diagram. This time the switch is on and VP is connected to the ground. Negative check. Is it negative? Yeah, the feedback is still negative. It is not affected by the switch. And then, by the summing point constraint, we know that VN equals to VP, and VP is connected to the ground here, so it's 0. And then, IN and IP equals to 0. Great, so we can compute that I2 equals to VN minus 0 over R. The current in the red branch is no longer 0 this time. Similarly, I1 is equal to VN minus VN, which is VN over R here. Right. And applying KCL at the non-inverting terminal, the inverting terminal, we know that I3 equals to I1, right? And then applying KVL from the start point, the star, to the end of the load, we derive that VO equals to minus I3, right? Which is minus VN over R times R, which is minus VN. In other words, AV equals to minus 1 here. Thus, we say that this circuit is inverting because it has a negative AV. What about the input resistance? Again, we still need the input current. The I of input equals to I1 plus I2, which is 2 VN over R. Input resistance equals to Vin over input current, and we get half of R as the input resistance. Great. So you'll see that with different circuit structures, it can be an inverting or non-inverting amplifier. It all depends on the final expression of your AV. Alright, that's the end of today's discussion. Hope you enjoy, and feel free to ask me questions. Thank you.